Thank you everyone for joining. It's my pleasure to introduce our last speaker of the quarter, Professor Ozdaglar from MIT. She's in the EECS department there and has been since 2003 and is currently the department head. She's affiliated with LIDS in the Operations Research Center, and her research focuses on problems that arise in the analysis and optimization of large-scale dynamic multi-agent network systems. And this includes communication networks, transportation networks, and even social and economic networks. For her work, Professor Ozdaglar has received a number of awards, including the NSF Career, the Class of 1943 Career Development Chair, as well as the Donald P. Ekman Award in 2008 for her contributions to control theory. And today we have the pleasure of hearing her speak about some of her recent work on robustness and machine learning. And so with that, I'll turn it over to you, Asi.
Thank you, Lillian. Thanks for the great invitation. It's great to be here virtually. It's great to see you all. Hopefully I'll be able to visit in person soon as well. So let me quickly start by sharing my screen and hopefully everything will go fine. Perfect. I can still see some people, which is essential because I can't give talks without seeing anybody. So as Lillian mentioned, I will talk about Minmax optimization today. It's a topic which is very dear to my heart, one that basically I've been working on even as part of my PhD, mostly from an optimization perspective, but it has attracted much recent attention because of robustness issues, generative models in machine learning. So what I'll try to do today is argue that Minmax formulations form a canonical backbone for designing robust algorithms to address these issues that I mentioned. And I will basically talk about some new algorithms, old algorithms actually, many of them are old, some systematic insights, connections, as well as some performance guarantees. And before I forget, this sort of is a body of work. I'll talk about a couple of different papers, and it's joined with some amazing researchers, Alireza Falla, Farzan Farnia, Sharat Patatil, all of whom are at MIT. Actually, Farzan is leaving soon to become a professor at CUHK, and Aryan Mokhtari, who was at MIT but is now at UT Austin. So very quickly, AI and machine learning methods, of course, are transforming our lives. They hold great promise in a number of important applications. These are the fun applications, reinforcement learning, image recognition, speech processing, but also safety critical applications ranging from self-driving cars to medical diagnostics. The success stories are fantastic, but of course, ML methods also fail drastically when they're deployed in environments that are different from those used in training. And here I basically highlighted three such changes. The first one relates to changes in the input data. Much of the literature here focused on the so-called adversarial examples, whereby these examples are perturbed images are generated by adding some imperceptible, very small, and carefully crafted worst case perturbations, and leading to these perturbed images sort of completely misleading the model and outputting incorrect answers with high accuracy. And there are many such fun examples in the literature, but this is just showing that those examples are not just of academic interest. And this is sort of an example where with very subtly altering the speed limit sign by sticking tiny stickers, Tesla's vision system can be misled to think that the speed limit is 85 instead of 35. The other, of course, change is when we actually train our models, using, for instance, in this example, classical images of traffic lights with vertical stands, and we still want the trained model to perform well under domain shifts, for instance, here, with horizontal traffic lights in Texas. And this is another example that shows that Google's medical AI actually, when you translate into real medical practices, sort of loses performance. And the other change that I wanted to highlight here is sort of different tasks that we may encounter over the course of the learning environment. And you see that, with object grasping, you have a model which performs with high accuracy, but with slight changes in the sort of task conditions, you see that, you lose accuracy significantly, sort of motivating the need for how do we actually make these models adapt to new environments. So that's sort of the robustness challenge. And I think throughout the talk, what I would like to highlight is optimization, and robust optimization in particular provides a systematic and principled approach for addressing some of these issues, sort of together with modeling and algorithm design during training, and also thinking about generalization performance of these algorithms. So most of the talk I will spend on a min-max approach to deal with perturbations, and talk about sort of convergence and stability of some min-max optimization algorithms, some of them very classical from 50s, but some of them those I learned a couple of years ago, which are fascinating. So I'll try to show you how these things relate to each other. And then I'll also talk about, much of the literature in this sort of ML optimization space focuses on sort of the stability properties of during training of these algorithms. But of course, we care in learning problems also how these trained models perform when you have unseen data sets or unseen environments. So I'll talk about sort of how we actually think about generalization properties of these min-max learning algorithms. And then at the end, I'll talk briefly about sort of this third shift in objectives. When you have multiple tasks, how do we think about task adaptation? And that sort of will be mostly, we'll talk about meta learning and particular approach for, there's a lot of approaches for meta learning, ranging from metric learning to others. So I will basically focus on, again, an optimization-based approach and a model agnostic approach, and I'll talk about that as in the second part of the talk. So let me start by the sort of min-max problems that I've been talking about. So as I mentioned, I view this as a very systematic canonical formulation for designing principled and efficient robust algorithms. And essentially the problem is, it's a very general class of problems where we're minimizing over X. X is our decision variable. Think about this as our model in the learning problems. Some objective functions f of x, y, which is parameterized by y, and we are interested in the objective, which is the worst case overall possible values of y. So what is the solution concept here? So we have it's not an optimization problem. So it's an equilibrium problem. And we're really looking at the saddle point of this function f, which is some x star, y star, such that x star minimizes over x when you fix y star, and then maximizes over y when you fix x star. So this is sort of the Nash equilibrium of the corresponding zero-sum game, or the saddle point of this function itself. And the sort of most classical, simplest algorithm, and probably most prominent, is the sort of this generalization of gradient descent, whereby we have two variables now, x and y. We're trying to minimize in one, maximizing the other. So we basically do that by taking the gradient descent steps in the negative of the gradient along x, and in the positive gradient along y simultaneously. And most of the time we can think about using a similar learning rate as the same learning rate, but also we can think about variations. So eta is the step size, constant step size or learning rate. And I just wanted to point out that this is like, the first time I learned about these methods, I basically learned them from this book by Arrow Hurwitz Uzawa. So it was not in the optimization literature. This is mathematical economics literature. beautiful collection of papers, which focuses primarily on how to sort of study these kinds of methods. They start from, thinking about continuous time versions. Most of the time, the assumptions are around strong convexity, strong concavity assumptions, and you can show convergence and some, global stability results under these kinds of assumptions. So, the reason I studied this in the past was, much more these kinds of problems, optimization, duality, how do we think about primal dual algorithms for resource allocation, primarily in the context of network optimization. But these problems came with a different light. You just fast forward 10 years or 10, 15 years even, now in machine learning with much more colorful pictures and very, very appealing. My son loves in particular, he saw this example. So let me first tell you the example. So you have this image of a pig, you sort of run it through a state-of-the-art classifier, classifies it with 91% accuracy as a pig. You add this imperceptible noise, you use the image is completely unchanged, but then you run it through your classifier, it classifies it as an airliner with 99% accuracy. So after this picture, my son, who was 9 years old, decided he's going to become a machine learning scientist. So there are many such examples that are very, interesting and cute. But of course, this will not be as cute if you're thinking about safety critical applications. So the question becomes, how do we actually protect our choice of our model against such perturbations? So there's a large literature on this, much of it empirical in the beginning, sort of through ad hoc attacks and defense mechanisms. All of this was formalized in a recent paper by Alexander Madry, my colleague, and his students using robust optimization. So to just put it in light, let's think about a special problem, classification problem. So let's assume that we have this distribution P, and this is over the pairs W, which is the input data. Theta is the corresponding labels. And we're interested in selecting a model X to minimize this expected loss. And loss function is basically what our model predicts and, with respect to what our training samples look like. So the robustified version of this problem is can be formulated as follows. We think about the input W being subject to perturbations. And it's, I think, it's actually very interesting, still ongoing question for me to think about how one should represent such perturbations. I think that's a very active and interesting area that ties to multiple different literatures. Here, Alexander and co-authors represented it as L-infinity perturbations. So assume that each of the pixels can be perturbed by little levels, Y. And then the robust training problem then amounts to now choosing again the model X to solve now a cost function, expected cost, but it's the maximum over this loss over allowable perturbations Y. So this is just to show that, in robust training really amounts to some min-max problem that one needs to solve to figure out what your optimal model should be. So the other place where this min-max formulations arise is the generative adversarial networks, GANs. Here the problem is, or the goal is learning the distribution of input data using observed samples x1 to xn. And the GAN approach formulates this problem as a zero-sum game between two neural networks. There's a generator, which is generating real-like fake samples from the random input. And then the discriminator is trying to distinguish between the generated samples and the real training data, real samples. When one sees this for the first time, I think it's a little bit, it was unclear to me at least how this min-max approach relates to this distribution learning problem. But actually one can show that this max objective can be written as a divergence measure between the input distribution and the generator distribution. So what this generator is trying to do is minimize this the divergence. And in particular, in the original paper of Goodfellow, the discriminator is cast as a as a classifier with some particular logistic loss cost function. And this maximization actually becomes one of minimizing the Jensen-Shannon divergence between these two distributions. So it's a min-max problem. There's a lot of theory behind it, but I mean also in the context of training, it's a very challenging problem because it's non-convex and non-concave, because when you actually parameterize this generator and distribution, the discriminator functions, they become sort of the weights of these neural networks. So it's basically a very complicated non-convex, non-concave problem. So when you actually try to train sort of these models using generally first order methods is the method of choice. So what you do is you minimize the generator using a single step of the gradient and maximize the discriminator for using a few steps of the few gradient steps. And you know, there's a lot of issues around instability. This is one instance sort of highlighting that instability. So the goal here is using as training data the celeb A data set, sort of the pictures of celebrities, and the goal is to generate like celebrity looking pictures, I guess, and these are people I guess, who look like celebrities. But basically the idea is when you start doing this min-max training, after a while, you sort of, all of a sudden, empirically, it's been observed that the output starts degrading significantly. So there's this instability issue, but also another one, which I'm not going to talk about in this talk, but one of great interest and relates again, I think, to optimization or algorithmic properties of the underlying problem is the mode collapse. And that is one of, you're interested in generating, let's say, these sets of bedroom pictures using some training data. Instead, what these GANs do is generate images which lack diversity. For instance, here you can show I guess you only have 3 types of images, so you only have 3 modes, and the others are not being excited by the output of the training algorithm. So these are all, I think, related to, so our goal was basically to step back and say what's going on here on the training algorithms, in particular this GDA algorithm. And even though it's very simple looking, innocent looking, algorithm, actually, even for some simple problems, if you have strong convexity, strong concavity, which was the literature I cited for you in the beginning, things work out, you have linear convergence, everything is beautiful. But if you don't have that, don't have the strong convexity properties, even for the simple bilinear case, you get divergence. And I just wanted to pick this example because this shows like very easily how things break down. So think about this problem of min-maxing x prime y. And here the solution is 0, 0. So this is where you want to go to. But if you apply gradient descent ascent for this problem, and remember it was updating x along the negative gradient with respect to x, which is for this function, gradient with respect to x is y. And gradient with respect to y is x, right? And then this is so simple that you don't even need to analyze. You can write down the iterates exactly. When you add these things up, take the norm squares and add them up, basically what you get is x plus y, x norm square plus y norm square on the left-hand side. And on this side, you have the x plus eta square, x square, and similarly y square. So eta square is positive, greater than 1. So this immediately shows us that this GDA actually, instead of going to 0, it diverges. So this is very annoying. So like, why is this happening? So I think I worked on this problem in the past, and with my co-author Angelina Nedic, we did work on convex-concave problems, and but I never realized this issue at the moment because we were always assuming compact sets, projections, or assuming bounded gradients assumptions, none of which is true here. So that's basically the problem. But in these kinds of problems, we have to deal with these kinds of issues. So there's a recent variant that I've learned about maybe 2-3 years ago when my colleague Kostis Daskalakis was presenting his results. He talked about the stability issues and then introduced OGDA, which is Optimistic Gradient Descent Ascent. It's basically GDA with negative momentum. And he basically presented it as this update rule, which is if you forget about the blue part. This is just GDA, right? It's GDA with a step size 2 eta. And then he said, well, I do a correction to this. I basically move to the back along the gradient of the previous point. So this is the pictorial representation. You move along the gradient, but then go back along the gradient at the previous point. And it's sort of, I think the pictorial representation tells you sort of this dampens the oscillation, but it was super interesting. And he said at the time, you know, it's important, actually, Sasha was on the Racklin was at the talk as well. It was important to get 2 times the step size and 1 times the step size here. So, I mean, that was very intriguing to us. So we started working on this problem then, and you know, then immediately. I was like, what is this? So we actually coupled papers at the same time. Sort of, we studied convergence results for bilinear as well as strongly convex, strongly concave cases, and then realized actually this was studied way before Sasha's paper, which was looking at these kinds of dynamics in the context of online learning by Popov in 80s. So, I mean, I think going back to the bilinear problem that I started from, you can just write down sort of this correction terms, and immediately it shows you that it does converge to 0. And then, so I want to just contrast it with another algorithm that, you know, you may have heard about before, the sort of the proximal point algorithm, which actually goes back to seminal work of Rockefeller from the 70s. So I will introduce sort of its form, you know, more exact form in a second, but basically what proximal point does is some future look ahead. So instead of, you know, doing the gradient at the current point, looks at the next point. And then, you know, it's generally sort of, it has this sort of a non-causal algorithm, right? You need to do some operator inversion. Its implementation it's sort of a conceptual algorithm in general. But for this simple problem, it takes this simple form because you can do inversion, you know, so everything is linear. So it shows you immediately that this is a contraction and actually beautifully goes to 0. And the interesting part on this problem, if you compare OGDA with proximal point, is OGDA is actually following proximal point very closely. So it's almost like an implementable version of this the convergence paths are very similar. So this realization was what motivated us to actually try to analyze or think about OGDA using this perspective. Can we think about it as an approximation of the proximal point method? So what I'll do next is actually show indeed that this viewpoint is powerful. If you look at OGDA as the approximate version of PP, proximal point, you can show that the iterates actually don't diverge. They're bounded and then they converge at a rate of O1/n. And then I will revisit another very, you know, popular method. Actually, it's a beautiful old method again, but became popular in these sort of training procedures. I will show that extragradient it's actually impossible, for me at least, impossible to remember because it's complicated steps. But I will show that basically that can also be viewed as an approximation of the proximal point. And then I will turn to, you know, this is all about optimization. I will turn and say, can we say something about the generalization properties of these min-max learning algorithms? And I will use a very powerful framework introduced by Bousquet and Elisseeff in 2002, which is the algorithmic stability framework. So I have to look at the time, but I think I can get, and then I will talk a little bit toward the end also on task adaptation. So just to go back to our formulation, we have this saddle point problem. I'm looking at the convex-concave case, and I will assume smoothness so that, you know, I can work with gradients as well as, you know, use the Lipschitz constant to control some of the step sizes and things like that. So X star, Y star is a saddle point. F star is our optimal. So we think about it as our optimal value. Okay, so proximal point, I talked already, but more generally, it's basically, this is actually generally known for the minimization problem. This is a min-max version of it. You min-max a modified objective function where the modification is some regularization around the current point. And in the convex-concave case that I'm considering, if you just take derivatives, first order optimality conditions of this problem, it exactly becomes this update that I told you about. You know, you basically do look ahead. You take steps along the gradient at the next point. Okay. And this is, I think, a classical result. You can find it in various papers that the iterates generated by the proximal point method, indeed, if you look at the, the duality gap, right? Sort of the value of the primal from F star and the dual from F star, that sort of converges to 0 at rate 1/n. These x hat and y hats are the averaged iterates. We're looking at ergodic averages, and d is basically the radius of the ball, sort of represents the distance from the initial point to the saddle point. So the realization, I think, for us that sort of made all these connections clear was the fact that proximal point strives to get this gradient at the next iterate. So I can actually think about approximating that by saying, I have my current iterate gradient, and let me actually use the increment of going from k minus 1 to k, add that increment to k and make it be the approximation at the next point. And if you do that, that's exactly OGDA. Remember, there was the 2. So if you actually do this approximation and add it, so you get 2 times the gradient at the current point, plus 1 times the plus the 1 times the gradient at the previous point. So this approximation of the next iterate gradient gives you basically the OGDA algorithm that was sort of studied in these different papers that I told you about. And then what we did is we used this exactly using this sort of viewing this as a proximal point with some error, an error given by the approximation error that I just showed you, to show that actually OGDA has the same iteration complexity of 1/n as proximal point, and it's an implementable version with similar convergence guarantees. So that sort of was the first thing I wanted to just talk about. And I will quickly, maybe in a few minutes, tell you how to sort of analyze this, because it's a very classical method of analyzing these kinds of methods. So very similar to how we analyze stochastic gradient descent, but this is just for the proximal version of it. And basically the idea is you view the method as proximal plus some error. And, this is just, cleaning up some notation here, but error for OGDA is something like this, difference between next point, current point, and the previous point. And this is sort of a key lemma or key relation for proximal point, in the Bertsekas book, it's referred to as the 3-term equality. So forget this red part, which is the part about error. Proximal point method, has this nice relation that is used in its convergence analysis. Basically, you can see that, you can introduce the error here, but once you see this sort of has this terms that sort of relates the current iterate with the next iterate, and then has some distance between the, next and the current iterate. So what you need to do to show sort of to extract a convergence rate from such a result is immediately, you just add this up, both of these sides, and telescope these terms, right? And once you do that, you add things from 0 to n minus 1, things telescope. This term is negative, so you can ignore that. And you get basically something like this. And then you open up the error term to actually get some relation like this. And then F, remember, is the gradients, and we assumed it's smooth, L smooth. So you can actually use the Lipschitzness here to write this as, again, related to Zn minus Dn minus 1. And then, if there's going to be an inner product here, you can approximate that term. But when you add up a little bit of algebra will give you basically this term here. And showing that actually using eta less than 1/2L, you do get, this is convex, right? So this has the monotone, this is, the F function is convex-concave. So that means that this capital F, which is the gradients, are monotone. So it's this inner product is non-negative. So you can actually put the Zn on the other side and immediately see that the iterates are bounded in this case. So that's sort of a classical way of analyzing these things and seeing the boundedness of these iterates. And then, the rest of, extracting a convergence rate for the ergodic average goes from, you look at this, this is an inner product between gradient and the z's. So you use the convexity to show that, to relate it to the value of the function. You were adding from 1 to n. Now you use the convexity of f to relate it to the function value at the ergodic iterate. And that's another trick we use to be able to get, that's why we use ergodic averages with this convexity concavity properties. And then when you put everything together, you basically get that 1 over n rate, which comes from, essentially this relation here. I hope it's clear. Maybe it's a bit technical. I think it's very good how things come together in the analysis of this kind of proximal point method. So you get the same convergence rate as the proximal point method is the point for the ergodic iterates. So let me then talk about Korpelevich's extragradient method, because this is also more and more used in many of these recent papers, and basically Korpelevich introduced it in '77 as a modification of the gradient method that uses the idea of extrapolation. Here is the updates of the extragradient method. I told you I can never remember it. Luckily, I finally did this figure, which allows me to remember it. So hopefully that will sort of stick in your minds as well. So what we do in the extragradient method is we're at a point x. And what does GDA do? You take a gradient at xk, and then you take a step along that gradient. So extragradient doesn't do that. It does it in 2 steps. First, generates a middle point by moving along the gradient, but then says, okay, I'm not gonna go to this point. I'm gonna evaluate the gradient at this middle point and move from my current point along that, middle point gradient. Okay, so it's sort of a way of, again, looking ahead, right? Like generating this midpoint and then moving along a gradient direction by this looked ahead gradient. So very similar, right? I mean, very similar to the ideas I've been talking about. The cute, I think another cute realization here is the fact that this is also very similar to a proximal point update. Namely, I'm not going to go over the details, it's a couple lines, but you can actually write down this EG updates by thinking about it as moving along these midpoints. So you get rid of the, current points, you just make it move along these midpoints. And then you can see that it takes this form. But then what are these update steps then? If you look at it, it's this gradient at -1/2 plus gradient from -1 to k. So that's actually can be viewed as an approximation of the gradient at k plus 1/2. So going back to this, if you actually substitute that approximation, then EG can be seen as approximately a proximal point update along these midpoint iterates. Is that point clear? I think, so I'm doing a lot of approximations, of course, but I think the idea is the same. You're just using sort of, looking back to be able to create a look ahead point approximately and then move along that direction. And if you actually put that idea and these error terms together and do the same type of analysis, you basically get, again, with some error constants and a convergence rate, which is 1/n. So let me make sure that, this is actually, Nemirovsky has looked in his seminal paper, has looked at EG as a special case of his Proximal algorithm and showed this 1/n rate for the case when the feasible set is compact using sort of a variation inequality type approach. Montero and Sveter extended this to unbounded sets using not the duality gap termination criterion, but something else. And this just shows a convergence rate of 1/n in terms of this primal dual gap. And I think using a very simple sort of connection to this proximal point methods. So this is what I want to say for this part of the talk. one thing I want to highlight before I move on to something else is these are all at ergodic averages. So we were also interested in sort of thinking about last iterate convergence for these methods. And that's, I mean, useful for various reasons. Many people are interested in this because, you know, most of the time we regularize these problems to maintain like some sparsity conditions, or, you know, the hope is that although everything here is convex-concave, we want to go to the non-convex-concave settings. So this ergodic average is very heavily using this convex-concave structure of the problem. So having some understanding of how the last iterate behaves is also important. So we have some results, both us and other groups, looking at the last iterate convergence behavior of these EG or GDA algorithms, but for lack of time, I decided to skip those parts. But very similar, I think, in spirit to things that I've been talking about. So let me move on next to talk a little bit about generalization properties, because everything in this literature seems to be focusing on convergence or local stability properties of these algorithms. But of course, we are interested, these are learning problems. We're interested in also seeing how they generalize. So the goal is here to see if we can come up with generalization bounds for these Minmax learning algorithms. And quickly, by generalization bound, I mean basically for Minmax problems, the expected difference between the error that a model incurs on the training set, like RZIs, I from 1 to n, minus the error it incurs on a new data point drawn from a distribution that generated the data set. So that's sort of the object, the generalization error that we're trying to bound. And you can talk about generalization error of an algorithm as, you know, exactly this, just, you know, replacing X, which is the model, as the learned model by this algorithm. And sort of, I think the framework we use to study Minmax algorithms here is, as I mentioned, the Bousquet and Elisseeff algorithmic stability, but it's also refined and studied in a beautiful paper by Hart, Recht, and Singer in 2016 to basically study generalization error of iterative algorithms. How can we relate algorithmic stability properties to sort of generalization? And the idea goes through this sort of notion of epsilon uniform stability of optimization algorithms. Basically, we say that a randomized algorithm is epsilon uniformly stable if for any two data sets that differ a little bit, it's just one sample, the learned models by this algorithm for these two different data sets do not, you know, the learned models do not, their approximations of the learned models are very similar. Okay, so the idea is basically if the input is close to each other, output will also be close to each other. So, and the reason why this property is important is this sort of very simple but very powerful result, which says that if an optimization algorithm satisfies such a stability property, then that immediately implies a generalization risk bound on the expected generalization risk, what I defined in the previous slide. So that means that we just need to understand this kind of stability property of the algorithm, what kind of epsilon stability it incurs to be able to provide a generalization bound on the risk that I've defined. So this is actually, this result is not hard to show. This was done very clearly in this paper by Ben and others. We just did it for, you know, min-max case instead of the minimization case. And it very much relies on the decomposition of empirical risk over individual data points, but it's also very powerful. We keep using it more and more for, you know, studying generalization of different kinds of problems and, you know, using sort of conceptually ideas from this framework. And this was just, I'm running out of time, so I don't want to spend too much time on this, but I learned this recently and I was very, fell in love with the idea very rapidly, because generally, you know, these generalization properties go through, you know, from in learning theory through, you know, this theory of uniform convergence of empirical quantities to their mean. So this is a little bit less powerful compared to that. We're not looking at uniform convergence. We're really looking at in expectation. How do we, how does this differ? And it's much more of an optimization viewpoint, I think, because it's very much a sensitivity-based approach. How much variation of input influences the output of a learning system, and moreover, it relates to like these seminal results in stochastic optimization, in particular the robust stochastic gradient descent or stochastic approximation results, where we're exactly measuring these kinds of differences, expectation of the population risk from the empirical risk, as seen by papers and books by Nemirovsky, Yudin, and co-authors. And the main key difference of this approach is that, in these, if you look at the stochastic optimization literature, these are all holding with fresh samples at every iteration. You assume that you get, you have this stochastic oracle, you keep getting a fresh point from that stochastic oracle at every point. Whereas, the way algorithmic stability is defined, it enables generalization bounds over multiple epochs of this algorithm over the training set, which is what is done in practice in machine learning, right? We don't, the Nemirovsky, like the stochastic optimization literature allows you to use every data point at most once in each stochastic gradient update, whereas here, which is consistent with practice, you can actually run multiple epochs or multiple passes over the training set. So by just combining stability and optimization errors together. Okay, so very quickly, I guess I will just tell you how this sort of can all be put together, or how we can actually analyze. So remember what I said was we need to understand whether an algorithm is epsilon uniformly stable, or what epsilon is it uniformly stable for. So meaning you apply this algorithm to two data sets that differ in one data point and how they diverge from each other, how their outputs diverge from each other. So to do that, we analyze basically how two different sequences of update rules diverge when iterated from the same starting point, but working on two very slightly different data sets. And for that, basically, the first thing to understand is to understand this expansivity property of a gradient-based update rule. And we say that, for instance, an update rule is gamma expansive when you apply the same update to two different points, you look at how much they diverge from each other. So their divergence is actually bounded from above by gamma. And this is a property. And then you can actually show that if you apply this in the context of gradient update rules, if you have smoothness in your problem, then it cannot be overly expansive because the gradients are bounded, right? Smoothness implies that. And then if you have strong convexity concavity, you can actually show that your gradient updates are contractive. This is exactly why, for strongly convex concavity, we have nice properties. For convex concave objective, this need not be contractive. It's actually could be expansive. So that's the problem with convex concave problems. But for proximal point method, it will again be not contractive, but non-expansive. Okay, I said a lot of things, it's impossible to digest, but I think I'm trying to make the point that these properties of smoothness, convexity, concavity, strongly convex, strong concavity, you apply it to gradient update rules, and that gives you different kinds of expansivity properties, which you can exploit to understand how these algorithms diverge from each other. So the other thing is, one thing is if you keep getting the same data points, you get the same gradients. So that's about how the same update rule diverges. But then at some point, you're going to pick this different data point, and that will be applying two different update rules for that just for that one step. So then one needs to understand, if you have gamma expansive updates, both the same algorithm, but it's G and G prime, how much you differ using a single update. And that's this sort of growth lemma that you show to show how using a single update rule, how much you can diverge from each other. So I'm not going to go into how to prove it. It's actually not too hard. Again, just, how gradient update, which is slightly different in gradients, diverge from each other in one step. But then to show the stability, it's particularly easy to see with SGDA. So you apply your algorithm to two data sets that differ in only one sample. For stochastic gradient descent, you select an example which is identical with probability 1 minus 1 over n, in which case iterates diverge only with the expansivity of the same update rule. Or you select with probability 1 over n, the non-identical example, and then you use the growth lemma, as well as, again, properties of the function. When you put together, you understand how these update rules diverge from each other. So that's sort of the approach for analyzing this stability property of the algorithm, and we now know how to relate it to the generalization. So where am I going to use all this in? I mean, this is the first place where we used it. I'm sure it's going to be used in many other places. And I'm very interested actually in seeing where else it can be used. What we did is we analyzed it to understand this behavior, generalization behavior of two different Minmax algorithms, which is GDA, which is what I talked about since the beginning of this talk, and the GDmax, which is another algorithm which a lot of people are using these days, which does a minimization in the X step, but some magical exact maximization in the Y step, okay? So GDA methods, for instance, are typically used for training GANs. Non-simultaneous GDmax seems to be the standard optimization method for adversarial training. Of course, you can't really get this maximization exactly, so they approximate it by, let's say, K steps. So and you can compare, optimization properties. What we want to do is understand the generalization properties of GDA and GDmax for strongly convex, strongly concave functions. And actually the paper has many different classes, but here I'm going to show you two results. One is the strongly convex case, and the other one is non-convex strongly concave case. And let's see if we have this strongly convex concave case. I'm running out of time, so I'll probably not spend too much time on this, but GDA and GDmax bounds, upper bounds, using our generalization analysis, seems to give you very similar results, just different by a constant factor of L over Lx. So there's some, I can explain where these constants are coming from, but it's basically just think about it as very similar for now. The interesting piece is, I think, when you go to the non-convex problems, then using this, different learning rates. You use a diminishing step size of 1 over t here, and then r square over t for the y step. And we have the result only for the stochastic case. We don't have the result for, batch case. But you can show that GDA and GDmax admit different upper bounds. And actually, if you use a learning rate R, which is less than this kappa is the condition number, which is mu over L, generalization bound for GDA seems to outperform the generalization bound for GDmax, which implies that simultaneous training somehow can lead to better generalization. So instead of non-simultaneous, you go much faster in Y, seems to give you, as opposed to, going with similar rates in the two cases, seems to give you better generalization. And this is sort of, I think there's much more to understand here, but theoretically supports, that was our motivation. There's a paper by Florian Schaefer and Anima and others that actually talks about this implicit competitive regularization, essentially saying that simultaneous gradient methods seems to perform better in training GANs. So this sort of provides some theoretical support for that observation. And we did some, simple numerical analysis to support some of these results. In particular, for the strongly convex, strongly concave case, we did not see much difference when we use non-simultaneous and simultaneous update rules. But very surprisingly, if you do this non-convex, non-concave cases, if you do 1-1 Adam, this is simultaneous update, versus 1/100 Adam. So think about this as a GDmax approximation. In the simultaneous update, training and test Minmax risks follow each other, implying, and then they go to 0, implying very good generalization performance, whereas things go completely wild if you change the optimization algorithm. So this red is the behavior on the training set, and the blue is the behavior on test set, which actually shows that there's a gap. I mean, this is clearly, the discriminator seems to be learning the training data, but not doing well at all on the test data. So why does this happen for non-convex problems? And, it's just, I think, tip of the iceberg type of thing. I can't explain. I have some vague explanations that I'm happy to share offline, but I mean, it's just super interesting to me that when you change the algorithms this way, where it's, in Minmax from simultaneous to non-simultaneous, somehow that does something different in exploring the landscape that has implications for the generalization properties. So, okay, so I am going fast because I want to use the next 10 minutes maybe to talk a little bit on the task adaptation, but maybe if there are any questions, I'm happy to stop. And
can I ask one quick one? So in
sure.
the theory result, was that for the exact oracle, or was that for like a k-step rollout on the inner problem?
It was for exact. It was for stochastic, but GDmax.
Okay, yeah, I'm just wondering if, how the results change if you actually study the like
k-step.
Yeah.
Yeah, I don't know. That's a good question.
Yeah, this is really interesting.
I am super interested and very also interested to talk to anybody who is interested in talking about this, because it's really unexpected. At least I don't have a very good, I don't feel like I have a very good understanding why this is happening. We see it numerically, other people have observed it empirically. This is how the result looks like if you apply algorithmic stability. It's very interesting. Okay. Super good. And I know a lot of people who are experts on these kinds of algorithm design problems here. So would love to talk to you offline about this. Okay, so let me move on to say a little bit about another area that sort of we got interested in lately, Alireza Falla in particular, and that's sort of this like thinking about task adaptation. And in particular, thinking about environments where we have multiple tasks. Potentially, think about robotics, robot is actually doing many tasks, learning at the same time, but may incur similar tasks as he continues to explore the environment. So the problem with those kinds of settings is that for new tasks that we encounter, they come with very limited labeled data. And that sort of I think I tried to emphasize before that we would like to be able to basically address this issue of, can we use prior knowledge and experience to sort of as a benchmark from which we can adapt to new tasks efficiently. And sort of the motivation comes from the fact that humans are very capable of doing this, right? So if you know how to ride a bike, if somebody gives you a motorcycle, you can actually, just from a few trials, be able to learn this new task, because you already have quite a good model for how to do that from your previous experience. So that's sort of the goal. And meta-learning, or learning to learn, is a framework that formalizes this idea to say, okay, I have actually experience from previous tasks, I had data from those tasks, I will use that to learn some update rules or models that then I can fine-tune or adapt later to new tasks, but using only a small amount of data. So that's sort of the notion of meta-learning. And essentially the idea is we train a common model using multiple tasks. And then we hope to update that model to a new task using only few data points from that task. Therefore, it also relates to this few-shot learning idea or on how to do few-shot learning. And basically our motivation was this beautiful work by Chelsea Finn, which is this so-called model agnostic meta-learning. And that's essentially this idea that you train using multiple tasks, and then you select the model parameters in such a way that you assume when the new task comes, you'll be able to have a budget to do a little bit of optimization, or a few gradient steps using a little bit of data from this new task so that you perform well on this new task. So it's basically pooling experience to come up with a common model, which can then be adapted using small amount of data. So that's the idea. I hope the idea is clear. How do you formulate this? Once we formulate it, it becomes a beautiful optimization problem, and then we're going to study that. And this is how we formulate this. For instance, sorry, I forgot to say one thing. It's called model agnostic because any learning procedure that is gradient based actually can use this idea. So I will talk mostly about supervised learning here, but this is also applicable in reinforcement learning or other types of approaches. So in supervised learning, how can we formulate the idea that I talked about? So think about number of tasks, TIs, coming from some distribution P, and assume Fi is the loss function corresponding to this task Ti. And the idea is, so you have a little budget to slightly update your model at test time. So how can we formulate this problem? Well, classical ERM, empirical risk minimization, is one where we're minimizing some expected loss, where the expectation is over all possible tasks drawn from this distribution P of these loss functions. Okay, so you just want to minimize this W common model, find a common model for all of these tasks that performs well on average. So now the MAML just differs by that slightly by assuming that, when the new task comes, you will be able to update that. And you can do this by a few gradient steps, but I think you can do the analysis, but just one gradient step is even enough to sort of illustrate some of the key ideas. So I'm going to assume here that the new task, when the new task arrives at test stage, we're able to do one step of gradient. Okay, so is the difference clear? So again, you're doing an expectation. So you have multiple tasks that are drawn from the distribution. Of course, you can't compute these expectations. We'll take batches over these distributions. But the key idea is the assumption that the shared model that you generate will be updated at test time using the specific properties of this new task. Okay, so that's the formulation. And then we can use gradient method to solve this MAML problem. So this is very classical. You have W, you update your W using a step size and a gradient of this F now. But what is this F? This F is that. But then, because it's this sort of a little bit more complicated objective function, the gradient of that becomes, you have to use the chain rule here, right? So you have I minus alpha gradient of this thing is Hessian of that thing, and then gradient of Fi times that thing. So that's just applying chain rule. And then this is your gradient step. And how do you implement this? You're going to get a lot of batches. You have to approximate this Hessian, you have to approximate this gradient, and you have to approximate this expectation. And you do that all by, either taking batches of data or by taking batches of tasks. And that's sort of MAML. You take a batch of IID tasks, you compute the stochastic gradient, you update by using exactly this update rule that I just talked about. Of course, you see here that MAML needs second order information. What Chelsea and co-authors did in that paper is ignore that and actually just ignore this and just do a first order version of that, because we don't want to deal with Hessians. But sort of the reason we got interested in this problem was if you actually, just empirically, you can show that if you do this kind of first order approximation, that comes with, basically that induces a non-vanishing error in the convergence properties of your algorithm. So what we did is very simple to address that. We just said, okay, instead of the Hessian, I just approximate it with first order differences. Okay, and that sort of gives the Hessian-free MAML algorithm. Nothing but just replacing this by this, approximation. I have talked about a lot of approximations in this talk. So this is just my approximation for second order information. And then, okay, I am super running out of time, but I want to just share with you, sort of for those, interested in, analysis of these kinds of algorithms. This is a gradient method. Even if I assume the little fi's are L smooth, the problem is I'm doing a gradient with respect to this capital F. And that capital F is not smooth. So that's actually, if you look at the Lipschitz property of that, the Lipschitz constant turns out to be some weird thing like this, which is actually unbounded. So to address that, we need to use an adaptive learning rate. And we need to compute this expectation over all tasks, which we cannot do, right? We're going to, again, take batches. So that makes the stochastic adaptive learning rate. And then we have to approximate all the errors and come up with estimates on those. So that's the first challenge. The second challenge is, when you're analyzing stochastic gradient descent, you have errors, but they're all unbiased, beautifully unbiased. The expectations cancel out. The problem here is that even though this thing is unbiased, it goes through this nonlinear function. So that makes it biased. So for instance, like the expectation doesn't go in, right? Therefore, the sample averages cannot be equal to the expectations for that reason. So you need to deal with the analysis as a biased stochastic method, but it's doable. So you can actually show some interesting results in terms of what you converge to. This is what I started by saying. The first order approximation actually does converge to, it doesn't converge to an arbitrarily close epsilon point. There is sort of an error level that it converges to, which is controlled by basically this sigma, which is sort of the task similarity. So if the tasks are very similar, this is small. But if they're not, this is large. And you can actually avoid that by using some of the other methods. And with respect between MAML and HF MAML, your runtime iteration, of course, this is a Hessian, that involves d-square iteration, d-square computation per iteration, whereas the Hessian free one only incurs d. So, and the final thing I want to say, and I will stop, is this idea of adaptation is also seems to be very interesting to use in federated learning settings, where you have multiple computing units or users, and each has little bit of data, and you want to pool this data to learn a shared model, but then you want to personalize, right? So actually, if you want to do this local fine-tuning, which is sort of the personalized federated learning, that's nothing but the MAML formulation is also very easy to use in that setting. So it's going to be a distributed MAML to be able to address this personalized federated learning problem. And then, this is again all for training algorithm performance, but one can actually look at now its generalization analysis along the same ideas that I talked about before. Okay, so with that, let me conclude. So I hope I was able to convince you that optimization and robust optimization plays sort of an important role in thinking about principled approaches to design sort of these robust algorithms for many learning problems, ranging from adversarial, GAN training, meta, multitask, federated few-shot learning, all kinds of learning. And what I showed here is basically to sort of some insights in terms of how these commonly used algorithms relate to each other. How do we analyze them? How do we provide generalization guarantees for them? I've mainly talked about convex-concave cases. We're barely touching this non-convex, strongly concave type of problems. And there's much interest and open questions for being able to generalize those to these non-convex, non-concave settings. But of course, this seems pretty hopeless. But at least when we have some structure that comes from the GAN problems or some other specific problems that we're thinking about, specific structural properties, can we say something in those cases? So that's sort of something of great interest both to our group as well as broadly in the community. And with that, maybe I'll just stop and see, Lillian, if there are any questions or.
Yeah, thanks. That's a fantastic talk. So I'll open it up we have time for a couple questions if people have any. Or please just unmute yourself and go ahead and ask.
I have a quick question. Thank you for the great talk. Yeah, a lot of interesting things, and I have a lot of questions, so I have to catch you later. But one quick question is, it shouldn't be difficult to change the step size eta to different step sizes for the X player and Y player, is that right?
Yeah. I mean, different learning rates, right? Yeah, absolutely.
Right. So different training, the analysis and convergence and so on goes through. So benefit from doing that, is there a benefit from choosing different step sizes?
Yes, because I mean, especially so, like if you think about GDA versus GDmax, right? You can think about the inside, right? That sort of faster learning.
Yeah,
that could be done either by K-step or by changing the learning rate. But then those changes affect properties. So it may help in optimization, it may hurt in generalization. So I think the point is we need to look at it holistically. And indeed, it may help in one dimension, but also we need to understand all these things. And then just I mean, I think even the other issues that in the non-convex setting, I think those play such interesting, weird roles because, the solution concept is not even well defined. This mode collapse issues, that also I think relates to these different learning rates and how one steers the algorithm in different places in the non-convex landscape. So I think the answer is it could help, but it could also hurt, I guess, if you don't do it properly.
Right. Yeah. Thank you.
Yes. We should talk.
Yeah.
More.
Lots of interesting
I
ideas.
know, I know.
Any other questions? So I'll just ask one quick one before we wrap up. So for the first part, I'm wondering if there's if you guys are thinking of, so you made a lot of nice connections between all these existing algorithms. And I'm wondering if you guys are thinking about, or whether there would be interest in having some sort of general framework that would, sort of be like a meta class of algorithms that can reduce to each of these individual algorithms, sort of of the flavor of like what folks did with symplectic optimization and, like the connections with like Nesterov and other.
For acceleration, yeah.
Yeah.
Yes, I haven't at all touched acceleration here, right? So that's, another set of questions. I think the only thing I did here is there are all these different types of algorithms that people seem to be using, at least in the convex-concave case. Look at it from this conceptual prox framework. And I think it's not super new idea, like this prox being a conceptual algorithm for these Minmax type of, this is sort of, I mentioned Nemirovsky also, probably in a variation inequalities, a lot of people looked at it in that light. So proximal point may be one that ties these things together, but I wouldn't call it like I think more we need to do like a continuous time approximations, maybe a way of going about thinking about a more unified framework for some of these things. The thing that motivated me was I was very annoyed why this step size has to be 2 times the other, because I had no idea why that. And it's not, right? Once you look at it from this perspective, you can actually see where are the limitations. Right. So I think the point of this was just to understand, can we look at this extrapolation idea in a systematic way, why we're doing this? And I think it's very much related to this look ahead idea. I don't even know if it's the prox, it's the look ahead.
Yeah.
And how you can approximate that. Which is, again, I mean, Mariam, an idea that's very, rollout and control, robust control. Like,
right. Like forward, backward Euler approximation.
Exactly.
Yeah.
Great point.
Okay. Thanks for this fantastic talk. You covered so many things.
Thanks for having me. This was great, and hope to see you all very soon. Thank you.
Yeah.
Thanks. Talk to you soon.
Thanks, everyone.
Bye-bye. Bye.